Hong Kong, as a metropolitan city, and its beautiful harbour attract myriads of tourists and businessmen every day. One of the most important assets of Hong Kong, the Victoria Harbour, is filled with rich collective memories of countless locals. However, due to the urban development and rapid population growth, the daily sewage produced has been polluting and deteriorating the water quality and marine ecology of our precious harbour. To improve the water quality of the harbour, the then Hong Kong government launched a sewage strategy study in 1987, with the aim of establishing water quality standard, protecting the coastal water in Hong Kong, as well as developing a long-term strategy for sewage treatment, including collecting, treating and discharging sewage in Hong Kong. The main report of the study was completed in 1989 with the following recommendations. 1. Improve the existing sewage collection and treatment system in Hong Kong. 2. Regulate the source of pollution and divert all sewage into proper disposal systems. 3. Construct an advanced sewage collection and treatment system at both sides of the Victoria Harbour. The report recommended a mega project called the Strategic Sewage Disposal Scheme, today known as the Harbour Area Treatment Scheme, HATS, to improve the water quality of the Victoria Harbour. The Drainage Services Department, established in 1989, is tasked with the implementation of HATS. This world-class sewage treatment project was implemented in stages. Stage 1 commenced in 1994. The works comprised of 4 major components, including 1. Construction of a sewage tunnel network. 2. Upgrading of 7 preliminary treatment works at both sides of the Victoria Harbour, namely Tseung Kwan O, Kwun Tong, To Kwa Wan, Kwai Chung, Xing Yi, Chai Wan and Shao Ki Wan. 3. Construction of Stonecutters Island sewage treatment works. 4. Construction of a 1.7 kilometre long outfall tunnel and diffuser pipeline in the southwest of Stonecutters Island. The Stage 1 construction costing $8.2 billion, and it was commissioned in 2001. It treats 75% of the sewage. Yet every day, 0.45 million cubic metre of ineffectively treated sewage was disposed into Victoria Harbour from the rest of Hong Kong Island, posing a threat to the water quality of Victoria Harbour. In addition, 7 beaches in Tsuen Wan were temporarily closed due to the non-disinfected sewage discharging into the sea. Therefore, while Stage 1 was put into operation, the government began to conduct a feasibility study on Stage 2. In 2004, planning, public consultation, design and environmental impact assessment for HATS Stage 2A commenced. The major works of HATS Stage 2A, costing about 17.5 billion Hong Kong dollars, commenced in 2009, with full commissioning in 2015, with the purpose of treating the remaining 25% of the sewage discharged into the harbour. The project comprised of 4 major components, including 1. Construction of a sewage conveyance system. 2. Upgrading of 8 preliminary treatment works in the northern and southwestern parts of Hong Kong Island. 3. Upgrading of Stonecutters Island sewage treatment works. 4. Construction of disinfection facilities. The sewage conveyance system comprises of a network of interconnected sewage tunnels and vertical shafts. Since the sewage tunnels pass through the compacted residential and commercial areas, adopting cut-and-cover method for the construction of the tunnels would cause major traffic impacts, which eventually caused inconvenience to the general public. Therefore, the sewage conveyance system adopted deep sewage tunnels option in order to minimize the impacts during the construction stage. The tunnel is 21 kilometers in length with depths varying from 70 meters to over 160 meters below sea level. To avoid any adverse effects on the existing building foundations and underground facilities, as well as the future development above the tunnel will have at least 30 meters rock cover. Moreover, the system works on the inverted siphon principle to minimize the downstream pumping depth and cost. During the design stage, reference had been made to the construction challenges during Stage 1, such as ground settlement due to the groundwater ingress and tunnel boring machines stuck in the fault zone. In this regard, geotechnical investigation was enhanced in Stage 2A by adopting horizontal drilling to collect soil and rock samples in order to understand the general geological profile of the tunnels. This helped to minimize the risks during construction. The drill and blast method with the aid of high-pressure grouting was adopted for constructing most of the larger diameter tunnel sections under the sewage conveyance system. The smaller diameter tunnel section from Applichow to Aberdeen was constructed by horizontal directional drilling with an accurate remote control on directional steering. Tunnel excavation works using the drill and blast method were carried out in cycles. Firstly, probe holes were drilled at the front of the tunnel excavation face to ascertain the ground conditions, and high-pressure grouting was applied. Blast holes were then drilled and explosives were charged to carry out blasting. After that, mucking out, scaling and installation of temporary supports were carried out. Tunnel excavation works, including investigation, grouting and drill and blast procedures, were carried out under precise design and close supervision of experienced engineers. Finally, more than 7,000 blasts were successfully completed for the construction of whole sewage tunnels. Since the tunnels are located at 160 meters below sea level, the groundwater pressure could be as high as 16 times of the atmosphere pressure. During tunnel excavation, ingress of large amount of groundwater was encountered. There was about 1,200 litre of groundwater coming out from a 2-inch drill hole in a minute. In order to control the ingress of groundwater effectively, high-pressure grouting was conducted before drill and blast. High-pressure grouting could fill up the rock fissures that prevented ingress of groundwater to the tunnels, as well as avoided ground settlement due to loss of groundwater. Meanwhile, parts of the deep sewage tunnels are located at the rock layer beneath the MTR tunnels. The tunnel's drilling and blasting works could not affect the normal operation of the MTR, posed the major challenges for the construction works. Therefore, close liaisons with MTR were carried out from planning, implementation, the drill and blast procedures, to completion of the tunnel excavation. In addition, advanced monitoring points were installed in the MTR tunnels to ensure the drill and blast procedures would not affect the train services. The Stage 1 and Stage 2A sewage conveyance systems convey all the sewage from both sides of the harbour to Stonecutters Island sewage treatment works for treatment every day. In order to prevent silt from accumulating in the deep sewage tunnels and protect the downstream sewage treatment facilities, sewage collected from both sides of the Victoria Harbour is first conveyed to the corresponding preliminary treatment works, where solid wastes and grits are removed. One of the major construction works of HAT Stage 2A was the upgrading of 8 preliminary treatment works at North Point, Wan Chai East, Central, Sandy Bay, Cyberport, Wafu, Aberdeen and Applichow. The works included demolition of existing treatment facilities and construction of new plants for installing more effective screenings and grit-removing equipment. The new fine screens with a spacing of 4 mm can remove solids larger than 4 mm in diameter. while the new grit traps can remove 95% of the grit with a diameter greater than 0.2 millimeters. After screening, the sewage enters the sewage deep tunnels via drop shafts. Each drop shaft has a vortex on top that can effectively change the direction of the sewage and hence reducing the momentum of the sewage flow. A vent pipe is also located on the top of each drop shaft that allows air in the sewage discharged. This prevents air from entering the drop shafts and tunnels that may interfere the operation of the conveyance system. In addition, the new plants are equipped with more effective deodorization units. Greening works were also carried out to integrate the plant with the nearby environment. Another core construction works of HAT Stage 2A was the upgrading of Stonecutters Island sewage treatment work. Utilizing state-of-the-art facilities and technologies, Stonecutters Island Sewage Treatment Works is known as one of the world's largest and most efficient chemically enhanced primary sewage treatment works. The upgrading works aim at enhancing and optimizing the treatment plant by increasing its Stage 1 treatment capacity from 1.7 million cubic meters to 2.45 million cubic meters per day, as well as constructing disinfection facilities. The highlight of the upgrading works is the new main pumping station, namely Main Pumping Station 2. It is the world's most powerful sewage pumping system in chemically enhanced primary treatment plant. Main Pumping Station number 2 is circular in shape, with a diameter of 55 meters and depth of 40 meters. When sewage arrives at Stonecutters Island Sewage Treatment Works, it is lifted by 8 new pumps in the main pumping station to the sedimentation tanks. These 8 pumps, each with a capacity of 4 cubic meters per second, together can dry up a standard swimming pool in 1 minute. Besides, the existing and new pumping stations are linked via an interconnected tunnel to enhance the operation flexibility and stability of the sewage treatment works. To increase the treatment capacity of Stonecutters Island Sewage Treatment Works, 8 sedimentation tanks were built in Stage 2A. The new sedimentation tanks are connected with the existing ones in order to treat all sewage from both sides of the Victoria Harbour. Sewage undergoes chemically enhanced primary treatment in the sedimentation tanks. Chemicals like ferric chloride and polymers are added to speed up the sedimentation process for removal of suspended solids and reduction of biochemical oxygen demand. To save space, double-deck sedimentation tanks are adopted. It is the most efficient use of land for providing chemically enhanced primary treatment. The sewage will stay in the tanks for about 1.5 hours until the solids in suspension have settled. The raw sludge is then conveyed to the sludge storage tanks for temporary storage. Apart from the sedimentation tanks, new dewatering facilities were built in Stage 2A to cope with the increased amount of sludge. The underground pipelines convey the raw sludge from the storage tanks to the sludge dewatering building, equipped with 14 centrifuges to remove water from the sludge. The solid content of the dewatered sludge will increase from 2% to 32% in order to meet the sludge incineration standard. The dewatered sludge is then conveyed to the sludge cake silos through solid pumps and unloaded to the enclosed sludge containers. The dewatered sludge is then conveyed to the sludge cake silos through solid pumps and unloaded to the enclosed sludge containers. The sludge containers are then delivered to the sludge treatment facilities in Chun Mun by marine vessels, Clean Harbour 1 and Clean Harbour 2, for further treatment. Clean Harbour 1 and Clean Harbour 2 adopt advanced maritime technologies, diesel-electric propulsion concept. With the aim of reducing the carbon footprint, the engine of the 2 vessels can enhance the fuel efficiency, and the vessels are propelled by electricity generated by using clean, ultra-low sulfur diesel during sailing. In addition, the vessels are connected to onshore power supply when berthed. No combustion of fuel is required, and therefore zero emissions can be achieved during berthing. Compared with the ordinary diesel vessels, the carbon dioxide emissions of Clean Harbour will be reduced by up to 130,000 kilograms per year, which is equivalent to the carbon dioxide absorption of about 6,000 trees per year. The construction of disinfection facilities is another focus of the upgrading works of Stonecutters Island Sewage Treatment Works. Stage 1 facilities could only reduce the suspended solids and biochemical oxygen demand in the sewage. However, the effluent still contained large amount of microorganisms that affect the marine environment. Therefore, disinfection facilities were constructed under Stage 2A to further improve the water quality of the Victoria Harbour. After sedimentation, the sewage is conveyed to the flow distribution chamber where chlorine, sodium hypochlorite, is added for disinfection. It is then discharged to the effluent tunnel and stays there for about 30 minutes for reduction of microorganisms by over 99%, before undergoing a dechlorination process by adding chemicals, sodium bisulfite, to neutralize the residual chlorine. Effluent is then discharged to the southwest part of Stonecutters Island via a submarine outfall constructed under Stage 1. The outfall itself comprises of twin risers, each with a diameter of 3.25 meters and diffusing pipelines with a total length of 1.2 kilometers. The discharged sewage is extensively dispersed to and diluted in the outer area of the harbour. Furthermore, deodorization units were installed under Stage 2A to treat and control the odour released from the sewage. All sedimentation tanks were enclosed and all potential odorous facilities were equipped with deodorization units to effectively minimize the odour nuisance caused to the nearby residents. The entire sewage treatment process is controlled by a distributed control system connected to the control system of each preliminary treatment works and Stonecutters Island treatment works, enabling overall supervision and automatic and manual control at Stonecutters Island Sewage Treatment Works to manage the whole process. The architectural design of Stonecutters Island Sewage Treatment Works adopted three major features, including environmental friendliness, durability, and aesthetic design. The roofs of some structures were built with recycled materials that were environmentally friendly, good-looking, and practical all at once. Efforts were made to keep the external design of the structures consistent with the style of the existing structures. Tricolour gravel was used to make a pictogram resembling the Chinese character for water, so that the external appearances of the structures look consistent. In addition, the conceptual design also referred to the garden layout. Green roofs are provided with various plant species to blend the buildings with the natural environment. Since the commissioning of HAT Stage 2A facilities, all sewage collected from both sides of the harbour is treated and disinfected before discharge. As a result, over 99% of the E. coli, 70% of biochemical oxygen demand, and 80% of suspended solids are removed from the sewage, which is equivalent to 800 to 1,000 tons of sludge recycled each day that were previously polluting Hong Kong waters. The cross-harbour race was resumed in the east of the harbour in 2011 after years of suspension, and the race was returned to its original route, the central part of Victoria Harbour, in 2017. Besides, the monitoring results from the Environmental Protection Department indicated that the water quality of the Chun Wan beaches has greatly improved, making it possible to gradually reopen the closed beaches. HAT Stage 2A is now fully commissioned. There is no doubt that the project is one of the largest sewage treatment works in the world. Its success does not only make Hong Kong people proud, but also further improve the water quality of the Victoria Harbour. It does not only promote the image of Hong Kong as a metropolitan city, but also offers the citizens a better living environment.